So now we're going to look at how we can predict the feasibility of reactions, or how we can predict whether certain reactions will occur or not. Okay, how we can predict whether certain reactions will take place or not by looking at the standard electrode potentials. Okay, so here we're going to be looking at how we can predict, predicting chemical reactions. Okay, predicting chemical reactions. Okay, and what we can say is that for a given reaction, if the potential calculated for that reaction is greater than 0, then we can say that the reaction will occur. Okay, and the reaction will occur. Okay, on the other hand, if the potential calculated for a reaction, okay, is lesser than 0, then we can say that the reaction will not occur. Okay, this is not exactly true. Okay, it's actually to do with feasibility. Okay, it's actually to do with feasibility. The more positive the potential for a reaction, the more feasible it is. The less positive or the more negative it is, the less feasible it is. Okay, so as an example, right, let's ask the question, will silver metal react with hydrochloric acid? That's the question. So the question is, okay, will this reaction take place, right? Will this reaction take place, right? That is, right? That's the question, right? Is this reaction going to take place or not? Right? So we don't know if this reaction will take place or not. We don't know if this reaction will take place or not. We have to determine that, right? Now, if you go to the data booklet, we have the two following half equations. We have the half equation for silver, right? That is Ag plus electron gives us silver, right? This has a standard potential of positive 0.80 volts. Okay, and the other reaction that we have is obviously the standard hydrogen half cell, right? And that would be H plus electron giving us hydrogen gas, right? And obviously we're going to have 2H plus and 2 electrons. And this has a standard value of 0.00 volts. Now here, of course, we don't have a cell. We just have to predict whether a reaction is taking place. Okay. Again, this is predicting chemical reactions, specifically predicting redox reactions. Okay. Predicting redox reactions using the values of the electrode potentials, right? So they've told us in this question, they've told us there are two reactants. The two reactants that we have are silver metal, right? Silver metal and H plus ions, right? Those are my reactants here. Silver metal and H plus ions, right? So we know for a fact, we want to know, okay, so that means if silver is reacting, right, that means if silver is reacting, it must be undergoing oxidation, right, to form Ag plus and electrons, and H plus must be undergoing reduction, right? So if you look at this half equation, right, what do we have? We have negative 0.8 for silver metal reacting, and for H plus undergoing reduction, we have a potential of 0.00 volts, right? So can I say that the overall E naught for my reaction is equal to negative 0.80 volts? Again, over here, they have already told us what our reactants are. They've told us that we're starting with H plus and silver. Okay, so unlike a voltaic cell where we determine which equations or which half equations are taking place, here they've already told us that we want the backward reaction for silver to take place and we want the forward reaction for H plus to take place, right? Which would mean that for the backward reaction of silver, my potential would be negative 0.8, and for the forward reaction for H plus, it would just be 0.00, right? Obviously, we can balance the electrons here as well, right? That would mean that the overall E naught, or the overall potential for this reaction would be negative 0.80 volts, right? Which means that the reaction will not occur. Okay, the reaction will not occur, or we can say that the reaction is not feasible. Okay, the reaction is not feasible. Okay, so we can say that that Ag will not react with Ag and HCl will not react. Okay, will not react because the value of the potential for the reaction is equal to negative 0.8 volts, right? So it's negative. Okay, so it's negative, and therefore the reaction will not occur. So over here, right, we know that the Gibbs free energy change for this reaction, delta G, the standard Gibbs free energy change for this reaction is equal to minus N F E naught, right? Again, N is the number of moles of electrons, F is Faraday's constant, that's the charge on 1 mole of electrons, and the E naught is the overall EMF of the reaction or the cell. So now over here, right, our Gibbs free energy change, delta G, is equal to minus N, the number of moles of electrons being exchanged, right? Here, looking at the stoichiometric coefficients, we know that we have 2 moles of silver reacting with 2 moles of H plus. That means the 2 moles of silver are losing 2 moles of electrons, and 2 moles of H plus would have been gaining 2 moles of electrons if this reaction were to take place. We know that it didn't take place, or it was non-feasible, it was infeasible, right? But we can say that the delta G is equal to then minus 2, right? That's the number of moles of electrons being exchanged, times Faraday's constant, that's 96,500, and then the E naught is negative 0.80 volts, right? And this comes out to positive 154,400 joules per mole. Okay. This will come out in joules because we're using coulombs and volts, right? Using coulombs and volts, so this value is in joules per mole. And then we can convert this to kilojoules per mole. The answer is positive 154.4 kilojoules per mole. Right? So that's the answer that we get. So then what we can say over here is the following. We can say that because the E naught is less than 0, the standard potential for this reaction is less than 0, which means that the standard Gibbs free energy change is greater than 0, and therefore we can say that the reaction is not feasible. The reaction is not feasible. Right, so there's a relationship between the standard reaction potential and the Gibbs free energy change. For energy changes, the coefficients in the equation represent the actual molar quantities. So when we're talking about energy changes, right, this 2:2 doesn't just represent the molar ratio, it means that 2 moles of silver are reacting with 2 moles of H plus. So therefore, we have 2 moles of electrons being exchanged. Okay. Again, for energy changes, the coefficients in the equation represent the actual quantities in moles. All right. So now let's find the standard Gibbs free energy change for the following reaction. Okay. Find the standard Gibbs free energy change for the following reaction. The reaction that we have here is the reaction between acidified manganate and Fe2 plus. Okay, so we have MnO4 minus plus 8H plus plus Fe2 plus. Okay, those are our reactants, and the products that we get are Fe3 plus Mn2 plus 4H2O. Okay, so we get H2O. So the coefficients that we have here are 1 mole of manganate reacting with 5 moles of Fe2 plus to form 5 moles of Fe3 plus, 1 mole of Mn2 plus, and 4 moles of H2O. So what we have to do here is we have to determine the half equations. We have to determine the half equations, right, for the reduction and oxidation in this reaction, right? Because we have a redox reaction, we have to determine the reduction and oxidation half equations, right? And we can do that by looking at the data booklet, right? We can do that by looking at the data booklet, and we have the following two equations, right? We have Fe3 plus electron giving us Fe2 plus, right? This has a standard electrode potential of positive 0.77 volts. The other half cell is an acidified manganate and Mn2 plus half cell, right? Acidified manganate and Mn2 plus half cell. So again, from the data booklet, right, we have MnO4 minus plus 8H plus 5 electrons, right, giving us Mn2 plus 4H2O, okay, plus 4H2O, right? And from the data booklet, the standard reduction potential for this half cell is positive 1.52 volts. So over here, looking at the overall equation, right? Looking at the overall equation, we can see that our reactants are manganate and Fe2 plus, right? So that means that manganate is undergoing reduction, right? Manganate will be the oxidizing agent, right, in this reaction, right? And now obviously Fe2 plus is the reducing agent, right? Fe2 plus is the reducing agent in this reaction. So that means we're going to be looking at the reverse reaction, right, for this half cell, right? So now we can calculate the EMF of the reaction, right? We can calculate the EMF of the reaction, that is equal to plus 1.52 minus 0.77, right? 1.52 minus 0.77. Again, this is a reaction that's reversing, right? So this will be negative 0.77. So over here, we can say that the standard potential for this reaction, right, the standard potential for this reaction is equal to positive 0.75 volts, right? Again, we had 1.52, that was for the reduction of manganate, right? And then negative 0.77, that is for the oxidation of iron 2 to iron 3, right? So therefore, the overall EMF of the reaction is positive 0.75 volts. The standard Gibbs free energy change is equal to negative NFE, right? Again, N is the number of moles of electrons, F is Faraday's constant, and then the E naught is the potential for the reaction or the cell. Now we have to determine the number of moles of electron. Now looking at the equation, right, the way the equation is given to us, we have 1 mole of manganate reacting with 5 moles of Fe2 plus, right? So here we're going to have 1, right? We have 1 mole of manganate and we're going to have 5 moles of Fe2 plus, right? Obviously the electrons have to be balanced. So we're going to have 5 moles of Fe2 plus, right? Now the electrons are balanced and we have the exact molar quantities in the half equations as we did in the overall equation. So that means we have 5 moles of electrons being exchanged. So N over here is equal to 5, right? So we have negative 5 times Faraday's constant, which is 96,500, times the EMF of the cell, which is positive 0.75. So this comes out to negative 361,875 joules per mole, right? So in kilojoules per mole, that would be negative 362, okay, to 3 significant figures. So that is roughly negative 362 kilojoules per mole. So that is the standard Gibbs free energy change for this reaction in kilojoules per mole. All right, that is the standard Gibbs free energy change. So again, we can say that because the EMF of this reaction was greater than 0, the standard Gibbs free energy change will be less than 0, and therefore we can say that the reaction is feasible.